Hello, February the 6th, 2024. It didn't take too long time to read section 4, but I actually haven't finished section 3 yet. You see, when I made these formulas that the forms must know or the functions must satisfy, it occurred to me that there might be a modular form of order unity with a single zero at Q. Yeah, so I would like to try and find that modular form to construct it if I can. So I've actually been I'm still working on that, and I will continue working on it during February. So I'll see if I can do it. But I think I should work on these problems as well. I actually did start, but then I had no sound recorded doing all this. Well, there's the Legendre symbol, which is defined for a prime and any integer here, which I'll take for given that we know the Legendre symbol and the reciprocity formula when C and D are prime. And that's, of course, positive primes. Then it's generalized to the Jacobi symbol, defined for all odd m and n, odd and positive, simply by extending multiplicativity. So we should prove that that has the same reciprocity. I've actually used that several times without realizing that I have only seen the proof of it for the Legendre symbol, so I haven't proved it. I tried to prove it this way, but it turned out that I'd forgotten to turn on the sound, and I don't like this method because it never became quite clear. So I tried to do it by induction on the number of primes in the denominator. That may actually not work. Because there is not a limit to the number of... Yeah, maybe that was a bad idea. Then maybe the longest set of primes. This argument, I didn't think I made it quite clear, so it would be a good idea to say we have it where the number of primes occurring is 1 maximal, and then we shall prove it for, assuming we have that, let's have one more prime on each, because then we don't have all these primes to work on, then it should be more clear. So let's do that. I'll just delete this and then do it on that page. So Jacobi symbol. And maybe it will become even more clear by adding one in the numerator and one in the denominator at a time. And that is, we assume that it holds for nm. And then we shall prove that it holds for n times some prime. Now, the definition of this and then we use the reciprocity. And then we multiply them together. So let's combine the possible residues of n, p, and m with respect to modulo 4. Let's do it alphabetically. M, N, P. So it's plus, plus, plus. And there are 8. In case it's they are all 1 modulo 4, it's the plus all the way through, so that's okay. When p is negative, then it's, if there's only one negative, then it's okay all the way through. Now, in this case, mn here, that gives a plus, and mp, that's a plus, and then np is positive, and m is positive, so it's a plus. In case m and p are negative, then it's a minus here, and mn is a plus, and then m is a minus and np is a minus, so that gives a plus. And here m, p are negative. Oh, that was weird. Oh, that was the one I made. Then m and n negative, that's a minus here, and a plus here, to give a minus here. M is negative and np is negative. And here it's minus all the way through, so it gives plus here. M is negative, but np is positive. So the signs do agree. And it will be the same when it's in the denominator. So that's a proof by induction on the length of the numerator and denominator. Then we come to the case where one of them is negative and one is positive. So D negative, C positive. By definition, this is equal to this symbol. Well, let's rather try the other one. Then the left-hand side is the same. The same as d modulo d over the absolute value of c. That's minus 1 over d times, that's the telephone. That took a while. It's now 1:45 p.m. I had to pick up my wife from the eye clinic. Nothing serious. Now this should be the absolute value of c. And that means that this changes sign, or rather change parity. Minus to this change parity if this is odd. So if this is even, nothing happens. If this is odd, then this change parity, but then this becomes minus 1, because then d is equivalent to minus 1 modulo 4, so this gives minus 1. So that means that we end up with the right formula. So that was an affirmation. And that actually finishes the proof of the reciprocity for the Jacobi symbol. If we take one of them negative, but we're already into the Kronecker symbol, of course. The Kronecker symbol is the one defined in the book, is in between the Jacobi and the Kronecker. This is defined also for m being even and naught. I don't know why naught is included, by the way. It solves the problem of a prime ideal, a rational prime, how that ideal splits in a quadratic extension of the rational numbers. So if it's naught, then p ramifies. If it's plus 1, it splits, and if it's minus 1, it's inert. So that solves the Kronecker symbol. I didn't know that. I know the Jacobi symbol, not the Kronecker. That was generalization I'd missed. But I read about the Artin symbol, which I believe is a generalization of the Kronecker, but then I didn't understand that very well. I didn't understand the use of it at all. Now, we are still lacking the case both C and D being negative. Now they have distinct signs. Oops, that was C over D. And we do the same trick. Maybe they could be combined somehow. because this is the same thing. Now it's just D that changed parity, and so the same argument goes. All right. Oops, I forgot the minus. So it becomes minus. Yeah, we got exactly the formula, never mind. So that proves this. And we don't need to take C or D being naught into consideration. They're both odd integers, of course. So that finishes problem 1.